Hi friends, this is Vishnu here. Welcome to my channel Tips, Tricks and Concepts by Vishnu. So in this video, I am going to continue with the topic of isomerism. Okay, so I am starting an important topic, that is geometrical isomerism. Okay, so this video is the very important part of isomerism, that is geometrical isomerism, especially cis-trans isomerism, about which I will give you all the relevant important points required for your exams, that is your NEET, JEE, etc. So please watch this video from the beginning to the end, because each and every point that I tell will be important and are required for you. So please make sure that you are very much thorough with this topic of geometrical isomerism. Okay, so let's go to the topic. So friends, in this video we will be learning about some important topics, that is cis-trans isomerism in some common compounds, then cis-trans isomerism in compounds containing C double bond N and N double bond N bonds, then the cis-trans isomerism in cyclic ring compounds, then the cis-trans isomerism around a single bond, then we will study the important point, that is how to find the number of geometrical isomers. Okay, how to find the number of geometrical isomerism when a particular compound is given. Okay, so we can easily find the number of cis-trans isomers when a compound, a molecular formula is given by just using a simple formula. Okay, so we will be studying that formula, and finally we will be dealing with the important properties of various cis-trans isomers which are usually asked for your exams, that is which of the following is more soluble, which of the following is having the greater boiling point, etc. Okay, so we will be studying all these in detail in this video. Okay, so first of all, let's go to the cis-trans isomerism in common compounds. Okay, so what is cis-trans isomerism, or what is geometrical isomerism? Okay, first we shall tell in general geometrical isomerism. Okay, cis-trans isomerism is not exactly what geometrical isomerism. Okay, cis-trans isomerism is just a single system. Okay, just a single system of our geometrical isomerism. Okay, actually the geometrical isomerism can be given in many systems, that is for example the cis-trans system, then EZ system, etc. So in this video we will be studying the cis-trans system alone. Okay, and I will be doing the EZ system, okay, Engegen and Zusammen system in the next video, which is also required for your exams. Okay, EZ system is not given in your textbook, but it has been asked in many entrance examinations. So firstly, what is geometrical isomerism? Okay, geometrical isomerism is nothing but the spatial arrangement of the atoms around a double bond. Okay, the spatial arrangement of the atoms or groups around a double bond. So if we look at the cause, we can see that the rotation of the atoms or groups around a double bond causes this geometrical isomerism. Okay, what was the case of our configurational isomerism in general? It was the rotation around a single bond. Okay, so as I have said before, this geometrical isomerism, the most common system of naming is as cis and trans isomers. So what is meant by cis isomer? Okay, so if the similar groups or similar atoms are present on the same side, okay, same side of the double bond, it is called as cis isomer. While if they are on the opposite side, okay, if the similar atoms are on the opposite sides of the double bond, carbon-carbon double bond, then it will be called as trans isomer. Okay, now what are the conditions of this cis-trans isomerism? Okay, what are the conditions for a compound to exhibit cis-trans isomerism? Okay, so the condition, the major condition is that each of the carbon atom, okay, each of the carbon atom of the double bond, okay, each of the double bonded carbon atom must have two different atoms or two different groups which may be the same or different for the two carbon atoms. Okay, so what is the essential condition for a compound to exhibit geometrical isomerism? Each of the carbon atom must have two different atoms or groups which may be different or the same for the two carbon atoms. Okay, so if A and B are two substituents, okay, are two groups or two atoms, then we can say that ABC double bond CAB, a molecule or a compound will exhibit geometrical isomerism, okay, be it cis trans or EZ isomerism, okay. So, and if they are different, okay, this is the case where the substituents on both the carbon atoms are same. Now we can see the cases where they are different, okay. So ABC double bond CAC will exist, okay, will have geometrical isomerism. Similarly, the compounds of the form ABC double bond CCD will exhibit geometrical isomerism. So let's make it clear by using some examples, okay. So let's take the compound of the form ABC double bond CAB, okay. So let's take the compound 1,2-dichloroethene, okay. So you can have this cis 1,2-dichloroethene as here and trans 1,2-dichloroethene as here. And nextly, we will take the compound of the form ABC double bond CAD, okay. So we can take the example of 1-phenyl prop-1-ene, okay. So we have cis 1-phenyl prop-1-ene as here and trans 1-phenyl prop-1-ene as here, okay. So these are some examples. Now let's see the second condition, okay, second condition regarding the exhibition of geometrical isomerism. So the compound will not show geometrical isomerism if the carbon atom, okay, if the double bonded carbon atom, if any one or both of the double bonded carbon atoms has both of its substituents, okay, both of its substituent as the same atom or same substituent or same group, okay. So I will tell it more clearly. If we have a double bond and then each of the carbon atom, if it is having the same substituent, then it will not show geometrical isomerism, any kind of geometrical isomerism, okay. It won't show any kind of geometrical isomerism. For example, let's take the case of propene, okay. So the case of propene, we have two hydrogen atoms are the substituents for one of the carbon atoms, okay, one of the double bonded carbon atoms. So it is having the same substituent and hence it won't show any kind of geometrical isomerism, okay. So propene won't show any kind of geometrical isomerism, okay. So these are the two essential conditions for exhibiting geometrical isomerism, okay. Now let's see the compounds containing C double bond N and N double bond N bonds, okay. So how do they exhibit geometrical isomerism and how we name them, okay, how we are going to name them as cis or trans, okay. Actually we are not using the words cis or trans, but instead we are using the word syn and anti, okay. That's the only difference, okay. Here in the similar way we are actually finding the more prior or more priority compounds, okay, more priority substituents, okay. So we have what compounds are having C double bond N? We are having aldoxymes and ketoxymes, okay. Just like in aldoxymes and ketoxymes, we are having C double bond N bonds. Similarly, we will have N double bond N bonds in azo compounds, okay. So we can see their naming with a few examples, okay. So the examples here are our benzaldoxime and azobenzene, okay. So firstly, let's take the case of benzaldoxime, okay. So in benzaldoxime, we have, this is the syn benzaldoxime. This is because here N has two substituents, right? Actually only one substituent, that is OH substituent, and the other part is actually a lone pair of electrons. So here how do we write syn and anti? That is nothing but those isomers, okay, those isomers in or aldoxymes or ketoxymes in which H and OH group are on the same side are termed as syn aldoxymes or syn ketoxymes, and the other compounds, okay, the other type of isomers in which the H and OH are on the opposite side, okay, or on the opposite side are termed as anti-aldoxymes or anti-ketoxymes, and hence it is named as syn benzaldoxime, okay. Similarly, if they are on the opposite sides, we will have it as anti-benzaldoxime as shown here. Similarly, we have syn-azobenzene, okay, syn-azobenzene as shown here, okay, and anti-azobenzene as shown here. That is, here we are looking at the phenyl groups. Okay, since the phenyl groups are on the same side of the N double bond N, we are calling it as syn-isobenzene. Okay, and if they are on the opposite sides, we call it as anti-isobenzene. Okay, that's all. Now let's go to the next topic, that is the cyclic ring compounds. How do they show geometrical isomerism? Okay, the geometrical isomerism is also shown by cycloalkanes. Okay, especially the di-substituted cycloalkanes. Okay, let's look at the examples. Okay, so we have our di-substituted cyclobutane showing our cis trans isomerism. That is, we have 1,2-dimethyl cyclobutane, that is showing cis and trans isomerism. Okay, cis and trans geometrical isomerism. And also we have another position isomer, that is for cyclobutane we have another di substitution possible, that is 1,3. Okay, so we have 1,3-dimethyl cyclobutane, which also shows geometrical isomerism as cis 1,3-dimethyl cyclobutane and trans 1,3-dimethyl cyclobutane. Okay, now nextly we can take the case of our cyclopropane. Okay, cyclopropane has only one di substitution. Okay, so 1,2 is only possible. So we can have the example of cyclopropane 1,2-dicarboxylic acid, and these are the cis and trans forms of our cyclopropane 1,2-dicarboxylic acid. And in a similar way, we have two possible combinations or two possible geometrical isomerisms for our cyclopentane also, because we have 1,2 and 1,3. Okay, 1,2 and 1,3 di substitutions are possible for cyclopentane, and hence we have our geometrical isomerism existing for each of these. Okay, 1,2 and 1,3 dimethyl cyclopentane. Okay, and the same thing occurs for our cyclohexane, which has actually three possibilities. Okay, 1,2, 1,3 and 1,4 di substitutions. Okay, and hence we have its cis trans isomers for each of these substitutions. Okay, each of these di substitutions. So why do the cyclic ring compounds show this geometrical isomerism? We know that it is having a single bond, so it would have shown configurational isomerism, right? But here it is showing geometrical isomerism because there is a hindering. Okay, there is a hindrance in the rotation of atoms or groups around this single bond in a cyclic ring compound. Okay, so we experience a similar hindrance as in the case of double bond in the case of our cyclic ring compounds. Okay, this is because if we consider a cyclic ring compound, say cyclopropane, and if we are rotating the substituents of any one carbon, then we are rotating it around a single bond. It is showing this geometrical isomerism. This is because when we rotate it, we experience the same hindrance as we rotate around a double bond. Okay, so we can say that this geometrical isomerism exists for our cyclic ring compounds too. Okay, actually it is a similar way. Okay, it is almost very similar to our configurational isomerism, which I have discussed in my previous video. Now let's see how a single bonded carbon atoms with double bonds on either side show geometrical isomerism. Okay, the example is as shown here. Okay, so we can see buta-1,3-diene. Okay, so here we have S-cis-1,3-butadiene where the double bonds are on the same side of the single bond, while we have S-trans-buta-1,3-diene where the double bonds are on the opposite sides of the single bond. Okay, so here the S in the prefix, okay, S cis stands for our single bond. Okay, so single bond cis, single bond trans. Okay, so that is a special case. Okay, now the major combinations, okay, the major compounds that can come for your exams are over. Now let's see how to find the number of geometrical isomers if a compound is given for your exams. Okay, how to find the number of isomers? We can easily find the isomers using a simple formula. Okay, so if our given compound is of the form ACH double bond CH single bond CH double bond CHB. Okay, so this A and B are any substituents, and we have this A and B consisting of some number of double bonds. Say we have totally n double bonds in this molecule, and we are using the terms A and B because we are denoting that on either side of this CH double bond CH, single bond CH double bond CH, we are having two different number of carbon atoms, okay, two asymmetrical molecule or asymmetrical substituents, okay, containing double bond. So here in this case of asymmetrical molecules, we can tell the number of geometrical isomers as 2 raised to n, okay, where n is a number of double bonds within this molecule, okay. So let's take a simple example, okay. So the example that I take here is our hepta-2,4-diene, okay, hepta-2,4-diene, and here if we look, we can see that instead of A we are having our CH3, and instead of B we are having CH2 CH3. So we are having two different groups, okay, two different groups on either side of our basic molecule, okay, basic structure, that is CH double bond CH single bond CH double bond CH, okay, that is the basic structure, and on both sides we are having two different groups, and hence if we count the total number of double bonds, we have 2 double bonds, and hence n is equal to 2. So 2 raised to 2, that is 4, okay, we have 4 geometrical isomers for this particular compound. But now a question arises, that is, what happens if both these atoms, okay, both these groups attached to this basic structure on either side of this basic structure are the same, okay. If they are the same, okay, if they are of the form A CH double bond CH single bond CH double bond CH A, then we have our formula as 2 raised to n minus 1 plus 2 raised to n by 2 minus 1, where n is even, that is the number of double bonds is an even number, okay, we have an even number of double bonds within this molecule, and if we have an odd number of double bonds within the molecule, that is if n is odd, then we have the formula as 2 raised to n minus 1 plus 2 raised to n minus 1 by 2, okay. So we can take the example of our chlorine, and then comes CH double bond CH single bond CH double bond CH single bond CH double bond CH, that is we have 3 double bonds with another chlorine atom, okay. So here we have on both sides, okay, on both sides we have the similar molecule, okay, we have the similar molecule, and since the number of double bonds is odd, we have the formula as 2 raised to n minus 1 plus 2 raised to n minus 1 by 2, and here we have 2 raised to 3 minus 1, that is 2 raised to 2, 4 plus 2 raised to 3 minus 1 by 2, that is 2. So we have 6 geometrical isomers totally possible for this compound. Now let's see the properties of these cis strands or the geometrical isomers in a little detail, okay, that's required for your exams, okay. So we are looking at the properties of then melting points, boiling points, then how to know which one is more soluble, that is the solubility of the isomers, then the dipole moments of the isomers, and various other chemical properties, okay, a few chemical properties. But before going to that properties, I have to tell you one important thing, that is this cis trans isomers or this geometrical isomers cannot interconvert in between, just like in our case of conformers, okay. In case of our conformers or rotational isomers, the torsional strain could be overcome with the kinetic energy among the molecules itself, okay. So the torsional strain was very small, but here it is actually have a double bond, and hence there is a pi bond overlap, okay. So there will be more stronger strain, and hence for this rotation of the atoms to take place, we have to provide some energy, okay. So at a particular temperature or at the room temperature in the environment, the compounds exist as only a particular more stable isomer, okay, either cis or trans, okay, only as either one, okay. This is because the kinetic energy among the molecules is not enough to overcome that torsion or overcome that rotational energy, okay, the repulsive interactions between the two substituents, okay, two carbon atoms. So now let's go to our properties, that is first of all let's deal with our melting point, okay. So we have trans isomers are having more melting point, okay, a higher melting point than that of the cis isomers. This is because trans isomers can fit very well in its crystal lattice than the cis isomers. So it is having a higher melting point. That is, we have to provide more energy to melt that solid, okay, to melt that compound. Okay, so trans isomer is having the higher melting points, and the reason is also told. Okay, it can be asked as a statement 1 and statement 2 questions. That is, statement 1 is correct and statement 2 as a reason, or assertion reason questions. Okay, assertion reason questions were actually asked in our AIMS exams. So since the AIMS has been integrated with this NEET, there are chances that assertion reason questions can also be asked. Okay, at least 1 or 2. Okay, so this type of questions, okay, this type of points can be asked as your assertion reason type questions. So let's look at an example. That is, we have malic acid and fumaric acid. Okay, so we have malic acid as the cis form, and the trans form is the fumaric acid or fumarate. Okay, so fumarate is having the higher melting point, as you can see here. Now, nextly, we can deal with our solubility. Okay, the property of solubility. Which one is more soluble? Okay, most of the time, cis isomers are more soluble than trans isomers. This is because of the same reason that I mentioned before. That is, trans isomers are very much stable or very well fits in its crystal lattice. Okay, while the cis isomers usually do not fit very well in its crystal lattice, so it can easily be soluble. Okay, such compounds can easily be soluble. Okay, and that's why you can see the solubility of your malic acid, that is a cis form, to be greater than that of our fumaric acid, which is the trans isomer. Okay, now that's all about solubility and melting point. Now we can go to our dipole moment, another important property that is often asked. Okay, so let's take the case of our 1,2-dichloroethane. Okay, 1,2-dichloroethane. And you can see the cis and trans forms and its dipole moments as shown in the figure. And you can see that in case of the cis form, the dipole, it is having a higher dipole moment. Okay, this is because they are towards the same direction, though they at an inclined at a particular angle. Okay, so here it is nearly 60-degree angle, and it is though it is inclined at an angle, the dipole moment is towards a single direction. Okay, so if it is towards like this, it will be its resultant dipole moment will be like this. But in the case of trans isomers, since they are opposite to each other, they can cancel out each other. Okay, here they completely cancel out each other, but in some other compounds as shown here, we have the dipole moments not exactly cancelling out, but still here also the trans isomer will be having lesser dipole moment than that of our cis isomer. Okay, that is in the case of our pent-2-ene. Okay, so here we have one side it is the methyl group, but on the other side it is the ethyl group. And as you know, their dipole moments, okay, dipole moments due to the methyl group and that due to the ethyl group are not exactly same, and hence though they are opposite, they do not cancel each other, but still, since they are opposite, the resultant will be less than that of the net dipole moment due to the cis isomer. Okay, so cis isomers are having the higher dipole moments. Now, nextly, we can go to the final physical property, that is the boiling point. Okay, here we have usually the cis isomers are having the higher boiling point than that of our trans isomer. This is because of a different reason, that is, the cis isomer, okay, this is isomers, as I have told before, is having the higher dipole moment, right? So the molecules among the cis isomers, okay, the dipole-dipole interactions among the cis isomers will be more than that among the trans isomers, because there is no dipole moment within that molecule, and hence there will be no polarity within that molecule, and hence there will be no dipole-dipole interactions among different molecules, right? I hope you have understood. That is, if we take many molecules together, actually since boiling and melting etc. some bulk phenomena, actually we have to consider the intermolecular forces of attraction, and here if we consider the main force, that is the dipole-dipole interactions of two different molecules, since the cis isomers are having its own dipole moments, they are polar molecules, and hence they can have strong dipole-dipole interactions among them. But in the case of trans isomers, they won't have any dipole-dipole interactions among them. Okay, no proper dipole-dipole interactions among them. Okay, so in short, what we can tell, that is cis isomers are having higher boiling points. Okay, so cis isomers are having higher dipole moments, higher boiling point and higher solubility. Okay, so trans isomers are having only higher melting points. Okay, and now we can tell one more thing and just complete this topic of cis trans isomer. That is nothing but the chemical property. That is very much less important. That is the cis and trans isomers or any two geometrical isomers can be easily distinguished with some chemical properties. Okay, with some chemical reactions and all. Okay, for example, if malic acid is heated at 423 Kelvin, then it loses a water molecule and becomes a malic anhydride. But the same reaction does not occur at 423 Kelvin for this fumarate. Okay, so fumarate does not form fumarate anhydride at this temperature. Okay, so that's the major difference. Okay, major difference in terms of chemical reaction. So I hope the topic is very much clear for you, and if you have any doubts, please feel free to ask me. Doubts can be messaged to this WhatsApp number, and as far as possible I will give you a faster reply. And so you have to very well remember the conditions for exhibiting this geometrical isomerism and how to name this as cis or trans or syn and anti and so on. Okay, so please make sure that you are very well thorough with this topic. Okay, so this topic is a very important topic that I have dealt with, and this video is also very much important. So please watch it till you become very much clear about this topic. Okay, so this is because the questions regarding the geometrical isomerism is very well repeatedly asked in many exams. So I am telling it again, please make sure that you are very well thorough with this topic of geometrical isomerism. Okay, so I will come up with new such videos on isomerism, and especially to complete this geometrical isomerism I have to take another topic also, that is EZ isomerism, which will be taken to you in a very small video. Okay, that is how to name the isomers as E isomer or Z isomer and so on. So till then, bye bye.